Hi everybody, welcome to the session. Today I'm going to be taking you through using FHIR terminology within data analytics. My name's John Grimes, I'm from CSIRO, Australia's National Science Agency. My job's to research new tools and techniques at the intersection of analytics and health data standards. I'm the lead on a project called Pathling that provides tools for transforming FHIR data at scale using Apache Spark. I'm also part of the group working on the SQL on FHIR standard. The way I'm going to structure this talk is to start by talking about the value of terminology knowledge for analytics and the types of information that can be taken from terminologies to enhance your data set. Then I'm going to discuss the FHIR terminology model and how terminology content can be mapped into this for a consistent interface. I'll also cover how you can query FHIR terminology using a server. Then we'll dive into how to run terminology queries across entire data sets and also how to represent terminology for machine learning applications. Terminology is used extensively within health data and is used to describe many concepts, including observations, diagnoses, procedures, medications, and many more. It's tempting to treat these codes as flat categorical features. However, there are many well-known terminologies in use within healthcare that contain lots of descriptive information about their codes. These terminologies can be seen as knowledge resources in their own right and can be used within analytics to add additional features to a coded dataset. I'm going to use SNOMED CT as an example of a particularly rich terminology that provides lots of information that we can make use of. This is a SNOMED CT code that might have been recorded as a diagnosis or finding, rheumatoid arthritis of left knee. If we look this code up within SNOMED CT, we find there is a great deal of information available to describe it. Hierarchy can describe the relationship between this concept and more general concepts or more specific concepts. This can be useful for capturing related data into categories. Attributes can describe things like the finding site, causative agent, and more. The hierarchy of concepts can be expanded out further to roll this condition up into even more general concepts such as arthritis or autoimmune disease. Unfortunately, there are a lot of terminologies in use in healthcare, and the information that they contain about their codes varies, as does the formats that they're distributed in. And this is just the well-known standard terminologies. As anyone who's ever worked on health data would know, there are also many local and proprietary code sets in use. To be able to consume the information within all these terminologies, you would have to learn and write code to consume all the different formats and concept models. Unless someone was kind enough to come up with a simple standard model that covered most terminology semantics. Thanks, FHIR community. FHIR has been built from the ground up with terminology as an important part of the specification, and part of this is a generic way to represent terminology within FHIR resources. This is a boon for analytics because it means that we can use standard tools to interrogate any terminology that has a FHIR rendering. Many well-known standard terminologies already have a FHIR rendering. You can find the official ones at terminology.hl7.org. For local and proprietary code systems, you can convert them into a FHIR code system resource yourself. To provide an example of how a real code system and its concepts map into the FHIR terminology model, let's continue with our SNOMED example. The hierarchy relationships we talked about earlier map onto parent and child properties in FHIR. There can be different hierarchy meanings for different terminologies, but for SNOMED, it's what we call a subsumption hierarchy, which means that rheumatoid arthritis is a type of autoimmune disease. These subsumption relationships can span multiple levels of the hierarchy, so it is just as true to say that rheumatoid arthritis of left knee is a type of autoimmune disease, and all the concepts in between. This becomes important when we want to find all the codes that are a subtype of another code. Attributes in SNOMED-CT become properties in FHIR, which is great because it allows us to access all these rich relationships in a standard way. Many terminologies have the concept of synonyms, including SNOMED-CT. These are presented as designations in FHIR. If the terminology has language translations within it, alternate terms are also presented as designations tagged with a particular language. In SNOMED-CT, even historical associations are made available through FHIR. These are the links that the authors create when they make changes to concepts. This can be useful to make sense of or find replacements for codes that have since been retired since the time of data capture. So if we do all this work to get our terminology into FHIR, what does this actually buy us? Once our terminology is in FHIR, we can call a set of standard operations within the FHIR Terminology Service API to answer questions about our codes. A FHIR terminology server can query the code systems, value sets, and concept maps that it knows about. It can also facilitate the authoring of terminology by allowing the user to write new resources in and update them. Now that we understand the type of information available through FHIR terminology, let's get into how to leverage this across our data sets for analytics and data science. These are some of the things we might be interested in accessing. We're going to cover properties or attributes of codes, synonyms, language translations, how to test value set membership, relationships between codes, and how to map between codes in different code systems. Pathling is a freely available open source tool that we developed at CSIRO to make it easier to use FHIR within data analytics. It enables numerous different use cases that involve the transformation of FHIR data. One of the things it can do is serve as the bridge between FHIR data and terminology by automating the task of making calls out to a FHIR terminology server and joining the results into your data. Libraries for Python and R are available for using this functionality within your data science workflow. You can follow the QR code on screen if you'd like to look at the Pathling documentation and get some more detail on what it can do and how to use it. These are the terminology functions that are available within Pathling. I'm going to quickly explain what they are and then I'll follow this with some examples of their use. Member of allows you to test whether a code is a member of a particular value set. Subsumes allows you to test whether a code is a subtype or supertype of another code. Translate allows you to translate between codes based on predefined maps. Property allows you to query properties or attributes of codes. Designation allows you to query text descriptions of codes, such as display terms, synonyms, and language translations. It's important to note that while Pathling is a tool for FHIR analytics, the terminology functions can be used with non-FHIR data sets. They're simply functions that can be used within SQL queries. This is an example of using the member of function against a SNOMED-CT-based value set. This data set is a simple tabular extract that you might get from a typical emergency department system. The first argument to the function is a column that contains the SNOMED-CT coding. The second argument is a FHIR value set that is known to the terminology server. In this case, it's a SNOMED-CT expression that describes concepts related to mental health. The result of this function is a true or false value against every code in the dataset. This could be useful for patient cohort selection or categorization of data. This is an example of using the translate function to convert codes from one code system to another. Here we're converting SNOMED CT diagnosis codes to ICD-10 based on a concept map that we've loaded into our terminology server. In FHIR, you can define concept maps with different equivalence types, and this function allows you to select which of these types will match. You can also optionally translate the map in reverse. This is an example of querying properties of codes. Here we're querying the finding site and associated morphology of each diagnosis code, and we've created 2 new columns to hold this information. This final example demonstrates the retrieval of synonyms. This could be useful for improving recall when using text matching searches over your data. So far, we've talked about querying aspects of terminology data and using them to add additional fields to your data set. This next section is going to talk about a slightly different take on this concept that is more applicable to machine learning. Feature engineering is a critical part of any sort of machine learning activity. At its essence, it's the application of domain knowledge to the task of translating raw data into numeric representations that can be used as inputs to model training and inference. There are many different methods that are commonly used to do this, and the methods vary according to the type of data that's being represented. A method that's commonly used to represent categorical variables, such as codes, is one-hot encoding. One-hot encoding involves creating a table where each distinct code has its own column. We simply put a 1 in the column that matches our code and a 0 in all other columns. Each code is treated as being independent and not having any sort of relationship to other codes. The encoding does not contain any additional information from the terminology itself. We can extend the one-hot approach to include features from the terminology, such as the hierarchy. In this example, we've added additional information to convert our one-hot into a multi-hot encoding. Both nocturnal angina and fascicular ventricular tachycardia now share a feature, as they are both types of heart disease. The presence of these features allows our model to learn associations with more general concepts than those that were directly captured within the data. Attributes and their values can also be encoded as features. Values of attributes can also have their own ancestor codes, which can be used to make associations with other codes that may not be directly related to them via subsumption. In this example, fascicular ventricular tachycardia has a finding site of left bundle branch structure. But because this is a structure of the heart, it also gets counted against this second feature that it shares with nocturnal angina. Use of these techniques can generate many additional features against your data. Evaluation is required to determine if these features are informative to the desired task. All the techniques discussed so far produce vectors that contain mostly zeros, with a few ones. These are also known as sparse vectors. Sparse vectors are extremely common in the field of machine learning, and techniques have been developed to represent them efficiently. For example, instead of using memory and computation for every column in the table, we can use the more concise convention of specifying just the positions that are set to 1. Dimensionality reduction techniques also exist for converting sparse vectors into smaller, dense vectors. Singular value decomposition, or SVD, is an example of an algorithm that can be used for this purpose. We often call these dense vectors embeddings, and they can have some nice properties like spatial proximity. Spatial proximity refers to the idea that an embedding that is similar in meaning to another embedding will be close to it in distance within the embedding space. This allows us to cluster similar embeddings and rank embeddings by similarity. This is a visualization of what it would look like if we took all the SNOMED CT diagnosis codes from a set of ED department encounters and reduce them to 3 dimensions. This results in similar encounters clustering together within the embedding space. The encounters have been colour-coded as orange for those that were admitted to hospital. If you can see that. We can zoom in and explore our embeddings to ensure that we're getting the correct groupings. Here we've identified a group of concepts that are all related to fracturing the neck of the femur, which is a common injury among the elderly. It looks like most of these cases are admitted to hospital. Another way to represent terminology concepts is to create an embedding of their natural language representations. This could include their preferred display terms, synonyms, or even textual descriptions of their attributes and relationships. Text embedding models can take a word, phrase, sentence, or even a whole paragraph and produce an embedding. This embedding is based on observations of similar pieces of text in context within large volumes of training data. Text embedding models have different capabilities depending on the character, quality, and volume of data that they've been trained on. Text embeddings can be used as an alternative to encoded relationship information, or they can work alongside. One recent innovation in text embedding models is instruction fine-tuning. This provides the capability to supply additional context to the model based upon the intended use of the embedding. In this example, dog bite is not really a diagnosis, but it is routinely captured using the diagnosis field in many emergency departments. The second example might be used to embed a free text note for a cohort search and selection use case. HTN means hypertension within the context of a clinical note, but it might mean something different in another context. CSIRO has released an open source library for encoding any type of FHIR terminology for machine learning applications. I encourage you to scan the QR code and check it out for more information. So to sum up, terminology features can be of great value to analytics and machine learning. A FHIR terminology server is a useful way to access this information. Pathling can serve as a bridge between your data and a FHIR terminology server. And the FHIR TX encoder can help you represent terminology for machine learning. Thanks very much for listening to my talk. I'd be happy to take any questions. Also, if you'd like to leave any feedback, you can use the DevDays feedback form using the QR code on screen. Thanks.
Thank you, John. Any questions?
Thank you very much for your talk and also for your service. I've been using your service many times. Thanks a lot. So one question that I have is it possible to call let's translate function in Pathling for multiple codes? Like imagine I have 1,000 codes that I want to translate from one terminology to another. Is it possible to, with one call, do it? And then how does it impact the performance? Even, even higher, like 1 million codes I want to translate. Because usually we do those in a relational table, which is much faster rather than doing it in FHIR. So is it scalable for applications like that?
Yeah, so first thing is you're never going to have 1 million distinct codes. So I think the most number of distinct codes I've seen in a large data set is more like around 10,000. So what Pathling does is it will only make the calls that it needs to make to satisfy that operation. So if there's only 1,000 distinct codes in your data set, it needs to make at most 1,000 calls. And it has a sort of smart caching mechanism that keeps that all close to where the computation is happening, and it can be invalidated by the server as well, because the server is the thing that knows when content gets updated. So the answer is yes, it can be run across any number of codes in your data set, but it's trimmed down to only the necessary operations that need to be done with the terminology server. Does that answer your question?
So that would be like 1,000 calls to the terminology server?
That's right, yep.
Expression like ECL, so you're calling for each concept?
Each distinct concept, yes.
You run like ECL, and getting concept and getting one by one. So let's say you're getting all the parents. All is A, like the whole chain. So you will get it in one call from server, or you will call it one by one? Get it one by one?
No, we call the server many times. In fact, we've implemented this numerous times. So one way of doing it is going to the server and getting an expansion and then joining that against the table and figuring out whether it's in that. But it's actually, in our experiments, we've found it to be more efficient overall to make multiple calls to the server. And it's also beneficial on the server side in terms of if you have a horizontally scaled out terminology server, those calls are less chunky to also share out to instances within that scaled out terminology server as well.
Thank you.
No more questions. Thank you, John.